Hello students, today we are going to take up the topic D and F block elements part 1. Under this topic we are going to discuss about the characteristic of transition elements. So let us start with a very good thought. We don't grow when things are easy, we grow when we face challenges. So challenges are part and parcel of our life. So learning outcome from this session is we will be able to explain about position of D and F block elements, electronic configuration, general characteristics like atomic and ionic radii, metallic properties, lattice structure, density, melting point, boiling point, enthalpy of atomization and ionization enthalpies. So let us start. As you know, D block, it is in between S and P, and F block, it is lying at the bottom of the periodic table. D block signifies the filling of D orbital. F block signifies the filling of F orbital. So if we see the position, left hand side we are having S block, right hand side we are having P block, and in between that that is D block, and these are also known as transition elements. Transition means change. Change from what? Change from the properties, from the most metallic to most non-metallic. If you see this, the S block is most metallic and P block is most non-metallic. So there is a transition in the properties like metallic character. Metallic character decreases, ionization energy increases, electron affinity increases, non-metallic character increases, reducing character decreases. So this is there are the transition in the properties. That's why that's known as transition element. Now here the general electronic configuration is, because the electron is filled in the n-1d subshell. That means if I am talking of ns means the outermost shell, and n-1 means the one less. If it is 4s, it would be 3d. If it is 5s, it would be 4d, and if it is 6s, it would be 5d. And if it is 7s, it would be 6d. So means to say that the filling of the D subshell takes place. This can be starting from 3d, 4d, 5d, 6d. This is the way how the filling takes place. Okay, similarly here n-2 filling takes place. So that is n-1 is known as penultimate and n-2 is known as anti-penultimate. So let us go in detail. So D block element, you know that D block elements where the last electron enters the D orbital, and general electronic configuration we have written here n-1 D 1 to 10, ns 1 to 2. Now all metals except mercury are solid at room temperature. It means mercury is a liquid. It's not signifying the property of a metal. That we will come to know little about. The zinc, cadmium, mercury, these are not known as transition element. Zinc, cadmium, mercury, the last three elements, zinc, cadmium, mercury of each series, 3d series, 4d series, 5d series, 6d series, these are series. So having 10 elements, this zinc, cadmium, mercury, they are not regarded as transition element because they are not having the properties similar to transition element. There are certain one more properties there. Definition is defined on the basis of that. So we will discuss in the next slides. So now here, these elements are having wide practical applications. Like for making coins, we are using copper, gold, and for making, let us say, catalyst, we need iron for Haber process, we need platinum for the Ostwald process. So wide variety of applications are there in the D block. They are very good catalytic properties. They are using in alloys. So these are very important, having practical applications. Now let us come to the basic definition of transition elements. What are transition elements? So first thing is that it is constituting D block. Fine, and D block is in between S and P. That's one. Second is there is a transition between the property from S to P, most metallic to least metallic, or most metallic to non-metallic. And because last electron enters the D subshell, D orbital, therefore they are known as D block elements. And now here in this, there are 4 transition series, 3D, 4D, 5D, 6D. And as you know that D orbital can have maximum of, there are 5 d orbital in a subshell. So one orbital can have maximum 2 electrons. So 5 into 2, 10. So each series having 10 elements. Now the point is definition. That a transition element is defined as the one which has incompletely filled d orbitals. So therefore d orbitals are incompletely filled. This is the prime condition in its ground state or in any of the oxidation state. For example, in Fe and Fe2 plus, Zn and Zn2 plus. So now, as we discussed earlier that zinc, cadmium, mercury are not regarded as transition element, we know their properties are not matching because mercury is liquid and iron is solid. Mercury is having low melting point, boiling point, and cadmium having low melting point, boiling point. Instead, copper is having high melting point, boiling point. So the point here is the properties are not matching. That's okay. But here, as per the definition, they are having completely filled d orbital. We can see the example here. Zinc electronic configuration is argon 18, 3d10, 4s2. So now this is the normal state and this is in the excited state, ionic state. So both of these states, they are having fully filled d orbitals. So therefore it is not regarded as transition elements. So very important question can be asked in your exam. Now, as we discussed earlier that d subshell are having 5 d orbitals and each orbital can have maximum of 2 electrons, so 5 into 2, 10. So it means each series, there are 4 transition series, 3D, 4D, 5D and 6D, they will be having 10 elements each because if the subsequent d subshells are filled, so there can maximum have 10 electrons, so therefore in a transition series, there are 10 elements. Starting from first series, that is known as 3D series, starting from scandium to zinc, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Similarly, 4D series there starting from yttrium to cadmium, and the third series, that is 5D series, starting from lanthanum to mercury, and 6D series starting from actinium 89, but 90 is not there. Please do remember. Rutherfordium 104 to 112. So these are the 40 elements comprising d block element in the 4 series that are known as first transition series 3D series, second transition series 4D, and then 5D and then 6D, each having 10 elements. 10 into 4, 40. Now these are the basic characteristics of transition elements. Like mercury is a liquid at room temperature while all other elements are solids. So they show variable oxidation state. For example, we know that Fe2 plus, Fe3 plus, copper plus 1, copper plus 2. There are some compounds which shows catalytic property. You know that vanadium pentaoxide, that is the catalyst used for contact process. Platinum, that is the catalyst used for Ostwald process. Finely divided iron, that is the catalyst used for Haber process. Finely divided nickel, that is the catalyst used for hydrogenation of oil. So I mean to say that these are having wide variety of catalytic properties. They show color also. So color compound like reddish brown is for ferric oxides. So this different chromium is showing color, manganese is showing color. So these are showing the color. Why? That we are discussing with the next part 2 video. They have great tendency to form complex compound. This also we will discuss in the next video and form interstitial alloys. Okay, let us now start with the very basic things. That is, first is electronic configuration. Now we should be aware of how to write the electronic configuration. All the rules in that of filling, like this rule we have done in +1, and in the basic principles of +1 that videos you can check. Everything is mentioned there. How to fill the electronic configuration as per the energy levels, following the 3 rules of a principle, Pauli's exclusion principle, and that pairing, Hund's rule of maximum multiplicity. So these rules we have to follow to fill the orbitals. So let us see here, scandium 21, 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, 4s2. Here 4s energy is less. First 4s orbitals are filled and then 3d. So 4s, because s orbital can have maximum 2 electron. First 2 electron will be filled in the 4s, then only 3d filling will start. Now you can see from here that scandium is involving 3d1 filling. Similarly, titanium filling is 3d2. Similarly, vanadium 3d3. But when you will see for chromium, it is not 3d4, it is 3d5. So these are two special cases for chromium and copper. Why it is so? Because we know that system of half filled and fully filled are extra stable. So this is half filled and this is fully filled. So system of half filled and fully filled are extra stable. Why? Because of maximum exchange energy. Because of maximum exchange energy, and the second reason is symmetry. This we have done in +1 also. So I would like to recommend you that you can pause the video and try to write the electronic configuration of each and every element of the D block and match with the book available, so that you can have more practice for the writing the electronic configuration. Okay, so now next coming out to the other characteristic, that are atomic and ionic radii, metallic properties and lattice structure, density, melting point, boiling point, enthalpy of atomization, ionization enthalpies. These things we are going to discuss. Rest of the properties will be taken up in the next video. So let us start with the first property, that is atomic and ionic radii. So see students, one thing is very clear, atom and ion. Radii means plural, and atom, like let us say zinc, and ion means zinc 2+. So this is the point. Ionic radii are always smaller than atomic radii. Okay. So now here you can see these curves here. If you talk of scandium, scandium is having 160 plus picometer, but zinc is having lesser atomic size. As you see from here, as you move from scandium to chromium, the atomic size is decreasing, and there is then regularity, or there is no much appreciable change is there. Then again copper zinc it is increasing. This is the normal trend we are finding in the 3 transition series. This is first 3D, this is second transition series 4D, and this is 5D. So now here what is happening? First of all, we know that atomic radii, if I compare with S or P block, it is having lesser size than S and more size than P. Okay. So what is the basic reason for that? So basic reason would be the nuclear charge. As the nuclear charge is increasing, the atomic size will decrease. That's one. But here some important point also you have to understand, that when you start filling, if you have seen here, the filling of which orbital takes place? Filling of 3D orbitals takes place, and 3D these are in which shell? It is not in outermost shell, it is in penultimate shell. So if I am talking of penultimate shell, 3D orbital filling takes place. They are having poor screening effect or poor shielding effect of the electrons. Now increase in atomic number or increase in nuclear charge, that will decrease the atomic size. That's okay, fine. But you can understand here that the shielding effect is also increasing, because as the electrons are filled in d orbitals, shielding effect is increasing, which is acting in a counter manner. Counter manner means it is opposing. So therefore the decrease should be there. Wherever decrease should be there from scandium to zinc, it's not decreasing. It is just getting stagnant, because the shielding effect counteracts the increase in the nuclear charge. This is the one reason for that. Now the question may arise, like at the end nickel, copper, zinc, why there is increase? How it is increasing? The answer lies here is because you know that if you see the electronic configuration, everything depends on electronic configuration. Here 3D5 is there. Here also 3D5, 3D6. 6 means pairing started. 7 pairing. And here 3 are paired. Here fully paired. And here also fully paired. So now when the pairing of the electrons takes place in the d orbitals, which causes repulsions, and these repulsions are greater than the attraction due to increase in nuclear charge, means to say that inter-electronic repulsions between the d electrons increases the increases the repulsions and they decrease what is happening is they are repelling and they are countering on the increase in nuclear charge. Means to say that the repulsion causes the increase in atomic size as compared to increase in nuclear charge. Means the effect of repulsions is more as compared to that of increase in nuclear charge, because increase in nuclear charge is decreasing the size and repulsions will increase the atomic size. Okay, so hopefully this is clear to you. Now one more thing I would like to tell you is there are certain see here area ionic, as we told earlier that metal and iron, the difference. See, if you talk of here, it is for let us say starting from scandium, titanium, vanadium. If you talk of vanadium here, 135 picometer and here it is 79. So mean to say that ionic size is always less than atomic. So now scandium to chromium, it is decreasing. Why? Because of increase in effective nuclear charge. Second is atomic size of iron cobalt nickel is almost same, because of the attraction due to increase in nuclear charge is cancelled by the repulsion because of increase in shielding factor, because the d orbitals filling takes place, which is having poor shielding. Third is copper and zinc have a higher size because the shielding effect increases and electron repulsions increases. So because this factor are opposing the decrease in atomic size due to increase in nuclear charge. So this concept we should read in a very good manner and understand in a very good manner to understand all the properties of transition elements. Now, so from here also you can check that the electronic configuration 3d14s2, 3d242, and here it is chromium 3d54s1, and then again here copper zinc 3d10 So now the next trend is like atomic radius 1.44 Armstrong and 1.36, 1.25, 1.27. Here they start increasing. So this increase is due to abnormal. So you will say, sir, so this is not having any pairing, but then also size is increasing. This is having abnormal size increase due to its peculiar lattice structure. Okay, and in that next is regarding to 1.25, 1.66. Here last is increasing. Okay, hopefully this is clear to you. The next is regarding to the metallic character. Transition element mostly are metallic, and it involves metallic bonding, and in collaboration with covalent bonding also will be there, and the filling of n-1 d orbitals takes place. And as you know that metal means malleable, metal means ductile, metal means high melting point, boiling point, metal means having the high tensile strength and thermal and electrical conductivity, and hard and brittle and partially filled d orbital, covalent bonding between metal atom through the atomic orbitals. Okay, so here also earlier we discussed already, zinc, cadmium, mercury is not included in this transition element because their properties are not matching, and moreover they are not having partially filled d orbitals, partially filled d electrons in the normal state and excited state. So now as comes to the structure, lattice structure, we are done in chapter number 1. So there are 3 types of cubic structure like SCC, BCC, FCC, and the packing also we discuss hexagonal closed packing and cubic closed packing. Depending upon that, most of these transition elements are having the cubic closed packing or hexagonal closed packing, and the structure involves are BCC, HCP and CCP. Okay. So next is regarding to density. Now here density means what? Basically definition of density is what? Density means the mass per unit volume. Mass per unit volume. Now here if you can see from here scandium is 3.43 and 4.167, and here this increasing and then decrease. Now see, increase in charge means increase in nuclear charge. Nuclear charge means nucleus. Nucleus means mass. Increase in mass takes place here. And volume is decreasing. Why volume is decreasing? Because atomic size is decreasing. But here what is happening is zinc is having large atomic size. So large atomic size means volume will be more. So volume increase in mass is less as compared to increase in volume. Therefore zinc is having lower density as compared to others. So that's what we have to like. Zinc, cadmium, mercury, they are not having the properties similar to that of transition element. Therefore we are saying that they are not regarded as transition element. Although d electron is being filled, but they are not having partially filled d orbitals. Okay, so now the next is the melting point, boiling point trend. Now see from here that, so titanium, vanadium, chromium, this is irregular trend of the melting point, it's not a regular trend, and the trend basically depends on the metallic bonding. So the tendency to form metallic bonding decides the strength of the metallic bond, and then therefore melting point. So see here, chromium, if you see the electronic configuration, if you remember, chromium 4s155 is having maximum unpaired d electrons, so which is helpful in the formation of metallic bond. So metallic bond is having more tendency to form metallic bond, or higher metallic bond tendency is there, so therefore melting point would be more. Similarly, manganese, I have already discussed you that this is a special case, this is having a peculiar lattice structure, so therefore the melting point is low. And iron, cobalt, platinum, nickel, this is having poor metallic character because of the tendency for formation of metallic bond. Because here what is happening is number of unpaired d electrons started decreasing, and if you are talking of zinc, cadmium, mercury, and this is having fully filled, that is having no d partially filled d electrons, so therefore tendency for metallic bonding is least in case of zinc, cadmium and mercury. So we have discussed already that manganese melting point is low because of complicated lattice structure. Melting point increases up to chromium maximum because of maximum number of unpaired electrons. As the pairing increases, the tendency to form metallic bonding decreases, therefore melting point, boiling point decreases. So we have discussed already all this thing. Melting boiling point is the basic tendencies based on the half filled d orbitals. The greater the number of electrons in the n-1 d orbital in a partial manner, so and in addition to ns electron, so this involves the interatomic metallic bonding. Because of stronger interatomic metallic bonding, transition elements having high melting point, boiling point. So now how metallic property characteristic affects other properties. So you know that the transition elements are very good metals and they form metallic bonding because of unpaired d electrons, and if they are having very good metallic properties, the density would be high, the enthalpy of atomization will be high, and they will be having high melting point and boiling point. So now we will talk about enthalpy of atomization. So the basic point here I would like to discuss is what is the enthalpy of atomization. Sometimes we are not clear that what is the meant for enthalpy of atomization. Enthalpy of atomization is nothing but, if we can say that this is the energy required to break the bonds. Okay. So energy required to break 1 mole of bond, that is called enthalpy of atomization. The unit should be kilojoule per mole. So now enthalpy of atomization depends on what? Enthalpy of atomization depends on the bonding. Bonding, which bonding? Metallic bonding. And metallic bonding depends on what? It depends on number of unpaired electron in the d subshell. So higher the value of enthalpy of atomization means that because of large number of unpaired d electrons are there, which results in higher metallic bonding. Therefore enthalpy of atomization will be more. And as you go down, means 3D, 4D. 3D, 4D transition is having more enthalpy of atomization. Okay, and large number of unpaired electrons results in stronger bonding, stronger metallic bonding, and therefore higher value of enthalpy of atomization. So see from here, so 3D, 4D transition is having more enthalpy of atomization. So if you see series 3D, 4D or 5D, higher the value of enthalpization is due to presence of large number of unpaired electrons in the atoms. Now, ionization energy. We are going to discuss about the topic ionization. We have discussed already about the electronic configuration. We have discussed about the radius. We have discussed about the density. We have discussed about the melting point. Now we are going to discuss about the first ionization energy. You will see that 631, 658 and kilojoule per mole, and here manganese is having high ionization energy. And similarly this is 759, and then here it was increased. Here this is what is happening is 631, 658, little bit increase, and this IS, and then again zinc is having the maximum ionization energy. So let us see and discuss more about ionization enthalpies. So you know that ionization energy is the amount of energy required to remove an electron from isolated neutral gaseous atom to form positive atom. So ionization energy of transition element is between those of S and P. Why? Because S is having larger atomic size and P is having least atomic size. So ionization energy depends on atomic size, therefore ionization energy is in between S and P. And what is that? Ionization energy of transition element increase in a period, although increase is not regular. So this we have discussed, seen also, if by seeing the practical values. If we are seeing this value, this is not regular. So this is first increasing and then sharp increase is there, and then sharp increase, then stagnant, and then decrease, and then increase, and this is not regular. Why? Because the electrons are filled progressively in the d subshell, and that is of penultimate shell, n-1. As d orbitals have poor shielding fact, the fact of increase in nuclear charge is opposed by screening fact. These two factors are opposing. If I am talking of increase in nuclear charge, size will decrease. And if I am talking of increase in screening fact, then I will say the size will decrease, because the shielding, because the nucleus will not shield, nucleus will not attract the electron outermost shell. So therefore atomic radius will not decrease. And in case of nuclear charge increasing, atomic radius will decrease. So atomic radius affect the ionization energy. So therefore this change is observed. This is not a regular change. So here ionization energy of 5D transition series is higher than 3D transition series and 4D transition series. Why? So we have seen that. So 3D transition series filled the 3D orbital, and then 4D, and then 5D. So 5D, before that 4F also will filling starts. So 4F also having peculiar shapes, which results into poor shielding factor. So there the reason is lanthanoid contraction. So we will discuss in more detail the lanthanoid contractors in the coming F block elements. But as far as just brief introduction is given, steady decrease in the atomic and ionic radii of transition matter as the atomic number increases. This is because of 4F filling. 4F. Because you know that if I am going to fill 5D, before that we have to fill 4F because of the energy difference. Energy is less for 4F and more for 5D. The contraction size is quite regular. This is called lanthanoid contraction. This is very important. We will discuss in the next, I think third video for that. On what ground would you say that scandium is a transition element while zinc is not? We have to write the electronic configuration here. If you see the electronic configuration, the electron is filled in the 3D1. This is having partially filled d orbitals. As opposite to zinc 30 is having 3D10. They are not having partially filled d orbital. Therefore, zinc cannot be regarded as transition element, because even in the excited state also it is not having partially filled d orbitals. Stable of +2. Now the next question is, D1 configuration is very unstable in ions. Why? So D1 configuration, you know that D1 will attain stability after losing one electron. It will attain D0 configuration. So therefore, what is going to happen is it will attain the stability. And hydration or latent energy is more than sufficient to remove the only one electron. Means the hydration energy released when that ion comes in contact with the moisture, it will release energy. So that energy is more than the energy given to remove the electron in ionization. So therefore, if they are having high tendency to lose electron, means low ionization energy, or we can say that it changes directly from D1 to D0. That means they will be losing electron, therefore they will be acting as a reducing agent. So next is question copper 128 picometer you can see, and zinc is 137. What is the reason for that? So because of the shielding factor increases and electron-electron repulsions, zinc is having correspondingly low ionization energy as compared to other elements in the series. It involves the removal of electron, which allows the production of stable D10. For example, if the electron is to be removed from 4s, the energy will be less. And if you are removing the electron from 3d, then energy will be more. So this is the point. The 4s 906 is there, and again 1734 is there. But if you want to remove the electron from like 3d or like 3 electrons you are going to remove, i.e. 3 you want, the ionization energy to be. So congratulations, you might be knowing all the answers, I'm sure. And let us repeat the thought: we don't grow when things are easy, we grow when we face challenges. Thank you.